Section 250.6, concerning objectionable currents, was first introduced in the 1940 National Electrical Code, or NEC. In that initial version, it was designated as Section 250-6. A notable revision occurred in the 1947 NEC, which led to the section being renamed to Section 250.6, specifically addressing objectionable current on grounding conductors. While the term objectionable current isn't explicitly defined within Section 250.6 itself or in the broader NEC, related sections offer valuable insights into what constitutes objectionable current in specific scenarios. Section 250.4 A5 defines objectionable current as currents that have the potential to cause overheating, ignition, or damage to nearby materials if the grounding path were to be interrupted. Furthermore, Section 250.53 B2 defines it as currents that could lead to a dangerous overvoltage on ungrounded conductors should the grounding path be compromised. Historically, the 1940 NEC, in its Section 250-6, stipulated that current on grounding conductors should not exceed 25 amps. The primary intent behind this limit was to prevent currents that might overheat or damage grounding conductors, thereby mitigating the risk of fire. However, the NEC has since evolved to acknowledge that currents on grounding conductors can indeed be higher under certain conditions, provided they are not deemed objectionable. For instance, the 2023 NEC in Section 250.6 permits currents of up to 200 amps on grounding conductors that are effectively isolated from adjacent conductors. In conclusion, the adoption of Section 250.6 in the 1940 NEC established a crucial framework for limiting objectionable currents on grounding conductors, primarily aimed at preventing overheating and associated fire hazards. Although the specific definition of objectionable current has remained relatively consistent, the NEC has expanded its guidance to provide clarity on what is considered objectionable within various contexts. Understanding the evolution and interpretation of Section 250.6 is essential for electrical professionals to ensure safety and compliance with the NEC. The term grounding conductor refers to a conductor used to connect equipment or the grounded circuit of a wiring system to a grounding electrode or electrodes. Its purpose is to provide a low impedance path for fault current to flow back to the source, facilitating the operation of overcurrent protective devices such as circuit breakers or fuses. Grounding conductors are typically made of copper or aluminum and are sized according to the requirements of the NEC. The NEC specifies the minimum size of grounding conductors based on the size of the overcurrent protective device protecting the circuit. This ensures that the grounding conductor can safely carry the maximum fault current that occur on the circuit. There are two main types of grounding conductors: equipment grounding conductors and grounded conductors. Equipment grounding conductors connect the non-current carrying metal parts of equipment, such as enclosures and raceways, to the grounding system. This helps to prevent electrical shock hazards by providing a path for fault current to flow back to the source, tripping the overcurrent protective device. Grounded conductors, also known as neutral conductors, are intentionally grounded conductors that carry current under normal operating conditions. They are typically connected to the grounding electrode at the service entrance of a building. Objectionable current, as it relates to grounding conductors, is current that flows on grounding conductors that is not the result of a fault or other abnormal condition. This current can be caused by a variety of factors, including inductive coupling, capacitive coupling, and ground loops. Objectionable current can cause a number of problems, including nuisance tripping of ground fault circuit interrupters, or GFCIs, overheating of grounding conductors, and interference with electronic equipment. Section 250.6 of the NEC addresses the issue of objectionable current on grounding conductors. It states that objectionable current shall not be permitted to flow on grounding conductors. However, the NEC recognizes that it is not always possible to eliminate all objectionable current on grounding conductors. Therefore, Section 250.6 provides guidance on how to minimize objectionable current and how to address it when it does occur. One way to minimize objectionable current is to ensure that all grounding connections are clean and tight. Loose or corroded connections can create resistance in the grounding path, which can increase the amount of objectionable current that flows. Another way to minimize objectionable current is to use proper wiring techniques. For example, running grounding conductors parallel to current-carrying conductors can help to reduce inductive coupling. In some cases, it may be necessary to isolate the grounding system from other metal objects, such as water pipes or gas pipes. This can help to prevent ground loops, which can be a source of objectionable current. If objectionable current is present on grounding conductors, it is important to identify the source of the current and take steps to eliminate it. This may involve troubleshooting the electrical system to find the source of the current, or it may involve installing additional grounding conductors or isolation devices. The NEC provides specific requirements for grounding and bonding electrical systems to ensure safety and minimize the risk of electrical shock. These requirements cover a wide range of topics, including the types of grounding electrodes that are permitted, the size of grounding conductors, and the methods for bonding metal parts of the electrical system. Grounding electrodes are typically metal rods, pipes, or plates that are buried in the earth. They provide a low impedance path for fault current to flow back to the source, facilitating the operation of overcurrent protective devices. The NEC specifies the minimum size and type of grounding electrode that must be used depending on the size of the electrical system and the type of soil. Grounding conductors must be sized according to the requirements of the NEC. The size of the grounding conductor is based on the size of the overcurrent protective device protecting the circuit. This ensures that the grounding conductor can safely carry the maximum fault current that could occur on the circuit. Bonding is the process of connecting together all metal parts of the electrical system, such as enclosures, raceways, and equipment. This helps to create a low impedance path for fault current to flow back to the source, minimizing the risk of electrical shock. The NEC provides specific requirements for bonding different types of metal parts of the electrical system. In addition to the requirements for grounding and bonding, the NEC also provides requirements for ground fault circuit interrupters, or GFCIs. GFCIs are devices that detect small amounts of current leakage to ground and interrupt the circuit, preventing electrical shock. GFCIs are required in certain locations, such as bathrooms, kitchens, and outdoor areas, where there is a higher risk of electrical shock. Understanding the requirements of the NEC for grounding, bonding, and GFCIs is essential for electrical professionals to ensure safety and minimize the risk of electrical shock. By following these requirements, electrical systems can be designed and installed to provide a safe and reliable source of power. The evolution of Section 250.6 of the NEC reflects the ongoing efforts to improve electrical safety and address new challenges in electrical systems. As technology advances and electrical systems become more complex, the NEC is continuously updated to reflect the latest knowledge and best practices. The original intent of Section 250.6 was to prevent objectionable current from flowing on grounding conductors, as this current could cause overheating and fire hazards. However, as electrical systems became more sophisticated, it became clear that it was not always possible to eliminate all objectionable current. Therefore, the NEC was revised to provide guidance on how to minimize objectionable current and how to address it when it does occur. One of the key changes to Section 250.6 over the years has been the recognition that some level of current on grounding conductors is acceptable, as long as it does not create a safety hazard. The NEC now allows for currents of up to 200 amps on grounding conductors that are effectively isolated from adjacent conductors. This allowance recognizes that in some cases it is more practical to allow a small amount of current to flow on the grounding conductor than to try to eliminate it completely. Another important change to Section 250.6 has been the emphasis on proper grounding and bonding techniques. The NEC provides detailed requirements for grounding and bonding electrical systems, and these requirements are designed to minimize the risk of objectionable current. By following these requirements, electrical professionals can help to ensure that electrical systems are safe and reliable. In addition to the changes to Section 250.6, the NEC has also added new requirements for ground fault circuit interrupters, or GFCIs. GFCIs are devices that detect small amounts of current leakage to ground and interrupt the circuit, preventing electrical shock. GFCIs are now required in a wide range of locations, including bathrooms, kitchens, and outdoor areas. The addition of GFCIs to the NEC has significantly improved electrical safety, as these devices can prevent electrical shocks that might not be detected by traditional overcurrent protective devices. The NEC is a dynamic document that is constantly evolving to reflect the latest knowledge and best practices in electrical safety. Electrical professionals must stay up to date on the latest changes to the NEC in order to ensure that they are designing and installing electrical systems that are safe and compliant. Understanding the history and evolution of Section 250.6 of the NEC is essential for electrical professionals to ensure that they are properly grounding and bonding electrical systems and minimizing the risk of objectionable current. By following the requirements of the NEC, electrical professionals can help to ensure that electrical systems are safe and reliable. The term effectively isolated is used in Section 250.6 of the NEC refers to a grounding conductor that is physically separated from other conductive materials in a way that minimizes the potential for objectionable current to flow. This isolation can be achieved by using non-conductive materials to support and insulate the grounding conductor, or by running the grounding conductor in a separate raceway or conduit. The purpose of effectively isolating the grounding conductor is to prevent inductive coupling or capacitive coupling from causing objectionable current to flow. Inductive coupling occurs when a grounding conductor runs parallel to a current-carrying conductor. The magnetic field produced by the current-carrying conductor can induce a voltage in the grounding conductor, which can cause current to flow. Capacitive coupling occurs when a grounding conductor is located near a conductive object. The conductive object can act as a capacitor, storing electrical charge. If the voltage in the conductive object changes, it can cause current to flow in the grounding conductor. By effectively isolating the grounding conductor, these coupling effects can be minimized, reducing the potential for objectionable current to flow. In order to be considered effectively isolated, a grounding conductor must meet certain requirements outlined in the NEC. These requirements specify the minimum distance that the grounding conductor must be separated from other conductive materials, as well as the types of materials that can be used to support and insulate the grounding conductor. The NEC also provides guidance on how to determine whether a grounding conductor is effectively isolated in a particular application. This may involve measuring the current flowing on the grounding conductor or using other methods to assess the potential for objectionable current to flow. The concept of effectively isolating grounding conductors is an important one for electrical safety. By properly isolating grounding conductors, electrical professionals can help to minimize the risk of objectionable current and ensure that electrical systems are safe and reliable. The NEC is constantly evolving to reflect the latest knowledge and best practices in electrical safety. As technology advances and electrical systems become more complex, the NEC is updated to address new challenges and ensure that electrical systems are designed and installed to provide a safe and reliable source of power. The reference to 25 amps in the 1940 NEC Section 250-6 as the maximum allowable current on grounding conductors highlights a significant early attempt to quantify and limit objectionable current. This threshold was intended to prevent overheating and potential fire hazards associated with excessive current flow on grounding paths. However, it's important to understand the context of this limitation within the electrical systems and grounding practices of that era. Electrical systems in the 1940s were generally simpler and less complex than modern systems. The types of equipment connected to these systems were also less sensitive to current fluctuations and electromagnetic interference. As a result, the 25 amps limit was considered a reasonable compromise between safety and practicality. Over time, as electrical systems evolved and became more sophisticated, the limitations of this fixed amperage threshold became apparent. The NEC recognized that a single amperage value could not adequately address the diverse range of grounding scenarios encountered in modern electrical installations. Factors such as the size and type of grounding conductor, the length of the grounding path, and the presence of sensitive electronic equipment all influence the potential for objectionable current to cause problems. As a result, the NEC shifted its focus from a fixed amperage limit to a more nuanced approach that emphasizes the elimination or mitigation of objectionable current, regardless of the specific amperage value. The current NEC recognizes that some level of current on grounding conductors is unavoidable in many electrical systems. The goal is not to eliminate all current flow, but rather to ensure that any current present does not create a safety hazard or interfere with the proper functioning of equipment. This is achieved through a combination of proper grounding and bonding techniques, the use of appropriate wiring methods, and the implementation of ground fault protection devices. The evolution from a fixed amperage limit to a more flexible approach reflects the ongoing efforts to improve electrical safety and adapt to the changing needs of modern electrical systems. By focusing on the underlying principles of grounding and bonding, the NEC provides a framework for electrical professionals to design and install systems that are both safe and reliable. The allowance of up to 200 amps on effectively isolated grounding conductors in the 2023 NEC Section 250.6 represents a significant departure from the earlier fixed amperage limit of 25 amps. This change reflects a better understanding of the behavior of current in grounding systems and the factors that contribute to objectionable current. The key concept behind this allowance is the idea of effective isolation. When a grounding conductor is effectively isolated from other conductive materials, the potential for objectionable current to flow is significantly reduced. This isolation can be achieved through a variety of methods, such as using non-conductive supports, running the grounding conductor in a separate raceway, or maintaining a sufficient distance from other conductive objects. By effectively isolating the grounding conductor, the current flow is primarily limited to fault current, which is the current that flows during a short circuit or ground fault. This fault current is necessary to trip the overcurrent protective device and clear out the fault. The 200 amps limit is based on the assumption that the grounding conductor is sized appropriately to handle the maximum fault current that could occur in the circuit. The NEC provides specific requirements for sizing grounding conductors based on the size of the overcurrent protective device protecting the circuit. In addition to the size of the grounding conductor, the length of the grounding path is also a factor in determining the allowable current. Longer grounding paths have higher impedance, which can limit the amount of fault current that can flow. The NEC takes this into account by requiring that grounding conductors be as short as possible. The allowance of up to 200 amps on effectively isolated grounding conductors is not a blanket exception. It is subject to certain conditions and limitations. Firstly, the grounding conductor must be effectively isolated from other conductive materials. Secondly, the grounding conductor must be sized appropriately to handle the maximum fault current that could occur in the circuit. Thirdly, the grounding path must be as short as possible. Finally, the installation must comply with all other applicable requirements of the NEC. This allowance is intended to provide flexibility in certain situations where it is not practical to eliminate all current flow on the grounding conductor. However, it is important to ensure that the installation meets all of the applicable requirements of the NEC to ensure safety and reliability. The NEC is a complex and comprehensive document that provides detailed requirements for electrical installations. It is essential for electrical professionals to have a thorough understanding of the NEC in order to design and install systems that are safe and compliant.